sort of introduce, no, spin it, so you can just see everyone.
Okay.
That's why we have it on a cart.
Oh.
So this is my grade 12 U chemistry class, and you can see the excitement and nervousness in their eyes. They're very worried about this, but I got a feeling this is going to go great. And I personally believe that I would much rather watch students and teachers actually engaged in real labs that they would do. And so we're hoping to bring that here. That being said, we did this unit about 6-7 weeks ago. So they're very nervous that they may have the odd error or something like that on the board. And maybe I might have threatened to go back and take marks off their own test if they did, if they embarrassed me, but we know that's not going to be the case. Yeah, there might be some times where they give me the look and I may have to hop in and tweak something on the board. But what I did for this unit was we started by looking at the practical aspects. So we're going to watch 3 different titrations. One's a strong acid, strong base. Then we're going to do a strong base, weak acid. And then we're going to do a buffer titration. And how I just decided to do it was instead of doing the theory first and showing it in the real world, we did the real world application first. So these guys spent almost 2 periods learning how to calibrate drop counters, learning how to calibrate pH probes. Sometimes it worked, sometimes it didn't. We had our own little hardware issues with some of our probes. The actual probe part wasn't working too well, and so you guys got very good at calibrating, right? Yeah.
Having Thomas in your group really helps.
Yeah. Some people may have tried to calibrate the same instrument like 4 or 5 times until we realized that maybe there was something wrong with the instrument. So that's okay. That's all part of learning. And as teachers, I don't think we should be afraid to create those opportunities where kids try stuff and sometimes it doesn't work perfectly. So what I'm going to do is I'm going to turn this over in a sec to my first group that are going to do strong acid, strong base. What they're going to do is not quite show it exactly the same way I did. They're going to explain the setup. They're going to get the titration started. They'll show you sort of what's happening on their iPad, which is what we did in class. And then they're going to jump to some of the board work that we did. What we did for class was we ran all these titrations, collected the data, analyzed the pH curves, and then went back the next day and proved the theories, or proved the real world experience. So why did we get the pH levels that we did when we did these things, and we did all that stoichiometry and acid-base equilibrium that way. We're going to kind of jump between the two just because we don't want to wait 10 minutes for a titration and then race through the explanation of it. So if I could get my first team up to bat here, and we'll let them take over. Yeah, so we have to open up. Okay, so maybe you guys could explain sort of what you're doing here.
So right now what we're doing is we're essentially preparing for the actual titration where we have the acid in the beaker and then we have the base in the actual titrant. So we have to get it so that the drops go at like an even rate into the acid, so you can see on the graph the fluid volume on the x-axis slowly increase as you level up the concentrations of the hydronium ions and the hydroxide ions.
Okay, and one thing just to let you guys know, I've learned a rule is that I pre-set up the bottom parts, which that sets up the flow rate. So the top is the on-off because it's a little sturdier. The bottom one is the flow rate, and I'm actually going to glue those things in right there so that they don't move because it gives a nice flow rate. And then that way they're all, when we go to calibrate it makes it easier to calibrate the volume. Okay. You just crank it on the button. Oh.
But this one here is.
Okay, so we just gotta, that obviously got tweaked a little bit. And that's okay.
There.
There we go. And so if you guys want to quickly talk about what you, and show that to the camera so people in TV land can see what's going on.
Okay.
Oh, maybe a little too
sorry.
close there.
Oh, I think that's good. That's pretty good.
Okay, so right now, we can see on the x-axis we have the fluid volume. So it should over time increase. Well, on the y-axis it should over time increase because right now we're adding more of a base which is higher on the pH scale. So over time, when we zoom out the graph, it should hopefully kind of skyrocket or exponentially grow, and then we can see eventually the equivalence point.
It'll go whoop.
Hopefully.
And that's the sound it makes, is a whoop. Okay, so while this is going, we actually watched it go in class, and the kids oohed and awed, which was awesome. We're going to sort of pause and take over and have Maya here explain some of the theory, the board work we did.
Okay, so this is our strong acid, strong base titration. So this is what we expect the graph to look like. Of course, data collection might be a little bit skewed, but the last time we did this titration, we had about 32.5 milliliters go into from the titrant into the beaker.
And I'm going to stop right there.
Okay.
So we knew it should have been 40 because how many mils did we put in to the bottom beaker? 40, right? But who prepared the sodium hydroxide? It was not me, right? Now, I prepared it today, but I prepared it very quickly. I didn't do volumetric class, so we're going to cross our fingers and hopefully get closer to 40. And then when we do, we can have fun with Mr. Seward, right? But he's retiring anyway, so he's old and he forgets things. If it's my fault, it's the kid's fault.
Okay, anyway. Let's pretend we didn't hear that. So we're starting with 40 milliliters of hydrochloric acid and 40 milliliters of sodium hydroxide. The sodium hydroxide is the titrant. And both of them are 0.1 molar solutions. And so we should be starting at a pH of 1 because that's the pH of HCl. And we should have an equivalence point of 7 when the graph goes whoop. Okay? And so it should be at 40 milliliters, 40 milliliters, but we're not quite sure. We'll see when the graph finishes. And I think that's almost about it. And at the equivalence point, the hydroxide ions and the hydronium ions should be the same, and that's why the equivalence point because they're equal.
Okay, if you guys want to show what's happening on the pH.
So right now, based off at the very beginning, we had a pH at about 1, which is fairly accurate for the acid. And now over time, we increase the volume. You can see that the pH is slowly rising because we're adding in a base into an acid. So when hopefully the 40 milliliters of the base does get into the beaker, we should see a nice exponential curve with a nice equivalence point at the pH of 7.
Okay, and what we can do is we can come back to this in a second and take a look at it. And again, nothing's ever perfect in the real world. But what I really like about using things like this is we can screenshot this, and I use these actual graphs when we went to do our unit test, which I think is more authentic. So when we go to do a test and I ask kids to identify the equivalence point and things like that, I actually use the graphs that we generated. And if you have this set up on your PC, I use the snipping tool. So I get my nice curve, I snipped it, and then I used like a little pen, which is easy. You can get writing pads or by Surface or something like that. And then you can write all over it and get the students to do that too. You can print these off and get the students to write over it because this is something they actually created. Thomas, you want to just show them what's happening right now?
So right now, what I was talking about earlier is right over here at about fluid volume of closer to 32 to 34, we have an exponential growth in terms of the pH. This is when we start to see the equivalence point form because the concentration of hydronium ions and hydroxide ions are eventually going to level out.
You should do the change in color.
Yeah. So what was the indicator we used here, guys? Yeah. And so what color was it before? Yellowish. And then once it turns, what's the color it turns when we hit equivalence points? Just does it for a split second.
Somewhere in the
Yellow to green, and then now it's blue telling us we are now we're now, alkaline. We've now gone past the equivalence point in that. Awesome. So thank you very much, guys. We are going to roll over to the strong base weak acid group. So we're going to get these guys to explain their setup and run it. And again, we had first done the strong acid, strong base. I tried to get the students to think about what a strong acid, how strong acid weak or strong base weak acid titration would work out. And then the next day we tried it out. And so we'll let you guys take over and explain.
Okay, so we have the same like basic standard setup as them for a titration lab. The only difference, like you said, was we're using a strong base, sodium hydroxide, and a weak acid, acetic acid. And we're basically just titrating the base into the acid and monitoring the pH difference on the iPad.
Okay, so hit the start.
We'll start now.
No, you gotta hit start first. Remember, hit start on the part view first. That always worries me it's not gonna work. And what indicator did I put in here? Now remember, for homework, what I told the kids was is that they had to pick the indicator and guess why. And I didn't say anything else other than that. And so I sort of forced them to try and do a little bit of pre-reading ahead of time to guess how a weak acid would interact with a strong base. So if you guys want to talk a little bit about what we're seeing here.
So it started before we started the titration. It started around 3.1 on the pH, sorry. But as you can see, the graph is slowly going up, and right now it's at 4.02. So we'll just let it titrate until the base, until the acid neutralizes.
Okay, and while that's happening, we'll get our team here to sort of explain some of the theory that we did in class.
So based off of what they said, it's a strong base and a weak acid, and that relates back to the equation. So we have the acetic acid and the sodium hydroxide reacting together, and that creates water and sodium acid.
Okay, so then we took the acetic acid and it reacted with water to create a hydronium ion and an acetate ion. And then we did an ice chart to figure out what the equilibrium moles per liter would be. And we knew the Ka value, so we put the Ka value and then the concentrations of each to find the concentration of the hydronium ion, which was 1.3 times 10 to the negative 3. And then we used the pH equation to find that the pH of this acetic acid at the beginning should be around 2.9, which it was with 3.1.
Okay, so continuing, we proved the equivalence point. We know based on theory that the equivalence point is around 9. So in order to do this, what we did, we broke down the sodium acetate, and we know that sodium is a neutral ion. So therefore, we assume that the acetate ion right here will react with water, and we have that equation right here written down. So we have the acetate ion reacting with water to form acetic acid and hydroxide ions. And like Maddie said before, we know that the acid constant is 1.8 times 10 to the negative 5. So we use this information to then solve for the constant of the base. And we can do this by using this formula written down right here, which is Kb equals Kw divided by Ka. And we know that Ka times Kb gives us Kw, which is equal to 1.0 times 10 to the negative 14. And when we did this calculation, we got that the base constant is equal to 5.55 times 10 to the negative 10. And then just like Maddie showed, we did another ice table. And here we have that the 5.5 times 10 to the negative 10 equals x squared. And then the 0.1. And we assume that it's 0.1 because when we divide the 0.1 by the acid constant, we get a number greater than 100. After we do that, we know
Greater
that...
than 1,000.
Greater than 1,000, sorry. After we do that, we know that the hydroxide concentration is equal to 7.45 times 10 to the negative 6. And we know that because of the molar ratios represented by this equation. So after we know that, we do the straight calculation of the pOH. And we know that pOH is equal to the negative log of the concentration of the hydroxide ions. And by doing that, we get a pOH of 5.13. And We also know that pH plus pOH gives us a total of 14. So then we use that equation to solve for the pH, and we get that the pH is 8.9. So when we did this titration, we proved that the equivalence point was reached at 8.9. And like Mr. Pila was saying, this proves that the actual indicator would be phenolphthalein because it has a range from 7 to 9. And we'll start to see actually the beaker right there. I don't know if you can see it, but it's starting to turn pink. And that's because of the indicator. So it's reaching that equivalence point, which we calculated to be 8.9.
Can we see?
There you go.
There you go. Okay, so we're almost at the point, and and we can see how high we are up on the pH scale. Again, what I love about using something like this is we can maneuver this around really easily. And how are we doing here, guys? Don't focus? Awesome. And so now we're seeing the big uptake, what the kids call the exponential turn in it, and it's going to shoot up.
They call it the whoop.
The whoop, sorry. That's the whoop. There it is. That's a 90s thing. Okay, and so we can tell now we've gone past the equivalence point, and if I pull the graph back, we can see we passed that equivalence point would be right around 9. It's a lot easier when there you go. So when I show the students this, we always cut it in the middle, and we can see that we're pretty much on between 8 and 9 right there. So the theory is the practical is being backed up by the theory on the board, which is pretty cool. Awesome. Okay. Again, this was really neat, especially because the shift, when we ran this, the students all found, for the most part, I noticed that they found it interesting that we had that shift, that the equivalence point wasn't the same. And because they get a chance to see it happening in real life, it tends to stick out a lot more. Of course, I could have given them handouts with this, but it's not as, it doesn't hit home as much. We'll get the kids to maybe talk a little bit more about the experience of doing this when we're done here. But I find that doing the practical test and then showing the theory behind it works better for me, at least, than doing the theory first and then showing the practical later. So we'll move on to the last group here. No pressure at all. Okay, so this is one I've done before, and I've done this with groups that are either chemistry groups. I've done this with grade 11, and I've done this with environmental science group. This is when we start to talk about buffers. So this is a real fun one, and I just kind of threw it together pretty quickly. But again, I think this hit home on how buffers work a little bit better than if we just did the theory. So I'll let you guys take it away and explain what's going on.
Right, so over here in this solution is 150 milliliters of water mixed with some calcium carbonate, just enough to make sure all the carbonate is dissolved. And over here is 55 milliliters of 1 molar hydrochloric acid.
Not 1 molar, 0.1.
0.1 molar
Yeah.
hydrochloric acid.
1 molar is pretty strong.
I know, that's what I was wondering.
No.
Anyway, we are planning to drip all the hydrochloric acid here into this solution here and find out and see how the pH curve looks like on the tablets as shown over here. And I'm rambling.
Okay, so start the. Wait, make sure it turns on. No. There we go.
Okay.
Yep, it's been. Really too fast. There you go. Oh, way too fast again.
What can I say? I'm a mess.
Okay. Well, there we go. We just had just showed what happens in the real world there. Maybe surgery. You need to work on your surgical hands there, but maybe not. Don't do any surgery on me. So we need obviously delicate hands to work with this, which is why I am going to glue these later in case Jeremy decides to play around with the flow rate. Anyways, if you guys can maybe step in and explain a little bit about what you see here or over there. Yeah.
Are you going to do this first?
Yeah. Well, why don't you do that part first?
Awesome. So right now we're just seeing like the pH going. It went up obviously just because of like the mishap, but that's okay. And so right now it's slowly just decreasing a little bit. I mean, I can't really zoom in with it, but yeah, like I'm nervous.
Basically, it's going to keep decreasing until it reaches
Yeah.
a point in which the pH has been lowered enough, and the buffer cancels out the remaining hydronium ions that are added to the solution, as we can see over there.
So up here, what we have is what's going on in that buffering system. So we have calcium carbonate, and it breaks up into its two ions. Calcium ion, which is a neutral ion, and its carbonate ion, which is basic, which really likes hydrogens. So it wants to gather all the hydrogens in the mix to make a basic solution. So what happens is that rate, when it goes into water, creates hydroxide. And then when the hydrochloric acid is introduced, it wants to make hydronium, which together those neutralize each other to make water, to keep the pH at 7.
Okay, so we did some calculations here. It's kind of all over. I apologize. To calculate what our pH should have been over here. So we used our KSP value for this up here, and we used like the ice table principles to figure out what our concentration of the CO3 minus 2 would be, and then using our KW equals Ka times Kb. We put in that value that we knew, and we found the Ka for acid, and we went through and solved that to find the concentration of the OH, and then we found the POH, and from that, the pH.
Oh. Okay. Well, this is perfect because sometimes in the real world things work and sometimes they don't. So for some reason, the one of the probes wasn't talking to the iPad. It may be because it's an older iPad. But we did watch this for a while, and we did the curve that you saw on the board was one that we saw, and we ended up going through a fair amount of acid before the buffer was finished. One of the things with this one is calcium carbonate doesn't dissolve very well. So if you put just a tiny bit in, what the students noticed was that after a while the solution was going more and more clear, right? Because that's the calcium carbonate dissolving into the solution. And then when it goes completely clear, that tells you that it's all been used up, and then the pH drops again because you're adding more HCl in. Of course, so your volume is so high that you'll never get the pH back down to 1, but it does drop down a little bit more. So this is a really good lab that you could do even without using the drop counter per se, even just running the pH probe and looking at visually for students in environmental science or grade 11 chemistry, just to show them, introduce them into the concept of the buffer set. All right, so at this point, maybe what I can do is get a few of the students just to talk a little bit about what their experience was like doing this. Of course, I haven't told any of them that I was going to do this, so I'm totally putting them on the spot right now. But it's sometimes nice to hear from the kids what they liked and what they found sort of worked and what didn't work, because I think we, as teachers, need to always be open to hearing those things, right? So if you guys want to turn it all the way around, and we've got Robin, why don't we get you to, maybe you and Amy, there you go.
I don't know what I didn't like. When we first ran the experiment, I felt that the actual setting up the Bluetooth part, that was kind of annoying because it kept not working the first time we did it. We spent 2 periods figuring out how it worked. So it would definitely have been nice if we got a little bit more time to maybe not necessarily do it hands-on, but figure out how to do it with a written piece of paper that showed us how to do it, so we could study that before it and actually know how to do it before we were just thrown into the lab. Mr. Pila obviously knew this, so he gave us plenty of time to figure it out. But the part I didn't like was definitely setting it up.
Yeah, I wasn't there when we actually set it up.
Oh, you did, yeah. That's right, Robin wasn't. So who can I pick on next here? Maybe you guys. There you go.
Thomas is our tech support, and I was definitely in his group. So that what Amy described was fortunately not my problem. It was sort of Thomas's.
I guess calibrating and stuff like that depends on. For one, it could be the actual probe that can affect it into. It could be your level with technology and stuff. Just doing basic troubleshooting, that could probably help it. I think because I was kind of in that era where I could quickly dive in and identify what was going wrong, and so I think I was turning pH probes on and off, seeing which one worked and which didn't. Even searching my iPads, I think I kind of figured out what worked and what didn't. So overall, the technology part of it went quite well for me, but I did other factors I could obviously.
Now, overall, guys, how did you find it? And be honest, I'm just going to pan around here and get the whole class here. You're going the wrong way. No. You guys got to be in the shot here. Get everyone in here. Yeah. Okay, so show of hands, how many of you, and I want you to be honest, found at some point during the lab when I asked you to do something and I just left you, how many of you found that uncomfortable? You're not quite sure, you were a little uneasy about it? Be honest. It was kind of fun.
Working with actors.
That's a fun one.
Experimenting on your own
How
being
did
able
class?
to work on your own.
Sorry, I say that.
Doing the experiment on your own and just trying to figure everything out by yourself, and then if you have any questions, you are there. Somebody was there.
Yeah, so during the lab, be honest, was I able to give 10, 15 minutes of my attention to each person? Yeah, but not for a whole block though, right? Because I'm walking around, so while I wasn't there, how did you guys problem solve? What did you do? Might have cried, yeah. Wait. Yeah, there was some patient
With our
waiting.
hands up.
I could kind of go off on what was due beforehand, and I would try to work based off what I knew from what you told me how to troubleshoot.
Mhm.
Going back and setting it. We reset it.
You went
Yeah, we reset it probably more than we actually did last.
we went through a bit of trial and error just to try to get the probes calibrated, but we tried multiple times to get them.
Now, what supports did I have set up for you guys ahead of time, right? So what did I post on Adsby, things like that to help
There
you?
was videos for to teach us how to calibrate things and how we should do the procedure. Also videos to understand what happens in the reaction. Yeah, as well.
So just for Pascal people, how did you like their videos that showed you how to set up and calibrate and
It
stuff?
was okay. It's just like
No, you're supposed to say it was amazing. It was super amazing.
Oh, totally.
Super great.
It's just it wasn't confusing that some of the iPads we looked at it were out of date.
Yeah, and that's
Let's go back.
that. Yeah, there you go.
It was the videos were very good in theory, but it just ended up working out a bit differently. Our page probes and stuff that didn't work.
Mhm.
That was a big. I think the videos themselves were good, in theory.
And they show clear instructions. It's just it didn't work on me.
And in context here, these pH probes have been used, some of them maybe 100 times, because I take my environmental science class in the field. Some of these probes are almost 3 years old, and I just didn't realize at the time that they have a shelf life. And one thing I also didn't realize is that, and for other people to know, is I try not to take the Bluetooth part on and off, which I was doing regularly. And so obviously there are some connections with the probes there. But again, that's all part of the learning. I think as teachers, we have to be okay with the fact that we're going to try something and it doesn't work out perfectly. And we learn learn alongside the kids. And I'm sure you guys will remember the times that Mr. Pilot was learning stuff beside you. Why is this not working? Oh, he's getting frustrated. But then realized it out, and we all kind of learned together. I think that's really important for teachers too, when we try and improve what we do, is that show students that we don't have to be the experts. Even though I tell them I know everything, I think they realize there's some things I am learning. Easy there. But I think this is really, really important. So what I'm going to say at this point is thank you guys really much. I'm going to sort of finish this off. If you guys could just grab the goggles, put everything on that last step. I'll clean up, but thank you guys so much for doing this. Really appreciate it. I'll take care of the acid and clean all that. And we'll just give them a second to get going because they got things to do. They're grade 12. They got exams coming up and stuff to go to. Just leave those there, guys, and I can take care of them. Yeah, okay. So Mr. Chikowski, yes, Okay, you guys just got to grab something? Yeah, all my stuff. Yeah, go grab your stuff. I'm just going to go over here and finish off. We'll see you guys later. Okay, so in a second, I'm going to give the power back to Rhonda. I just want to talk about a couple things once everyone's cleared out, just real fast there. So one of the things that doing activities like this can do is they can give teachers an opportunity to assess students, assess their problem-solving skills, and assess their actual skills in the lab. One of the things that I'll share with everyone in an email is the actual assessment chart that I came up with. These guys worked so well, there was no way I couldn't give them all perfect on the actual processing skills of doing this. And because this was a learning lab, there was no lab report. That the concepts we covered in assignments and tests later on. This was just, can you go, can you learn, can you show proficiency with doing calibration for the pH probe, calibrating the drop counter, using the equipment effectively and safely. And so what I'll do is I'll share with the group some simple assessment forms that allow students to know exactly what I'm expecting of them and how well they carried that out. And when you have classes, grade 9 and grade 10 classes, especially applied, the more opportunities you can get them to work with this equipment. So my grade 9s or my grade 10s work with pH probes. They learn how to calibrate it. There's no reason why they can't because those videos are great. And yeah, there may be certain issues along the way with our screens may look different or the probes don't quite, aren't maybe calibrating the way that the kids want to. That's all part of the experience of learning. So I just want to say thank you to everyone again for spending the time. I heard we had a whack of people come and watch this. The kids were really nervous, but this is going to help improve their learning. I think more often we need to give students these high pressure situations where they have to step their game up. And so I look for these opportunities. Just like when we're doing the lab, they watch the video, they get started, and then I walk away and see if they can problem solve. And of course I loop back to give them a hand, but I need them to work on their own. And some students like doing that, some don't, but that's a lifelong skill that every student needs to develop. So again, thank you very much. I'm going to see if Rhonda can take over now. And if you guys, or if you have any questions, maybe we'll switch to that. I'm just going to try and take it off the webcam here, and because I feel weird speaking like this, and we'll go from there.